Okay, so welcome to Homeomorphic Formations Intelligence of Everyday Life Objects workshop in Digital Futures 2022. So we'll be together during these 3 days. And as you see, we're 5 architects who are specialized in architecture, computational design fields, basically. And we have 3 days. And today we will introduce you topology, homeomorphism, AI, ML, and GAN. And then we will work on data gathering and processing. And you will be assigned for data gathering and processing everyday life objects. You will make photo shoots during, at home after the workshop. And what we aim for during the workshop, we have some objectives. Orkun Hocam, if we can pass to, yes. Yeah. So today we will introduce you the basic vocabulary of artificial intelligence, and you will be introduced to basic knowledge on data gathering and processing, and you will be introduced to everyday life objects, topological relationships. So what is topology, what is homomorphism? We will talk about those, and afterwards you will examine it. And this was a brief intro.
I'm going to start with the first part, which is the introduction of topology and homeomorphism. I think it's a quite difficult task, to talk about like facts. So like no more, not much like interpretation is possible here. So I'm going to go with it. So what is topology? It's sometimes mixed with typology, but topology is a combination of like place and study. So like work of place, so to work with places. So it's a field of geometry that is related with qualities of the geometry. So regardless of their like shapes and sizes, I think it can be taught about like 1D shapes, 2D shapes, 3D shapes, maybe like 0D shapes as well. So this is also good information about topology. So it works with like the properties of the geometric forms, and even there is a even there is a continuous transformation. The properties of the shapes remain constant. Yeah, and then if we like stretch, curve, or cut one shape to another, they might be still topologically equivalent. So what is that? So here we see a square and a circle, and they are both made of like 4 points. So even we change the shape, the organization of this A, B, C, D, like their order and their relation, their like links are still same. And what are the other qualities? Like, which is like being a closed polygon, like both of them. Okay, the circle is not a polygon, but they are like both closed shaped, and they are both not intersecting with itself. So this is a like example of topology. So this is a metro map, which one of this is warp on the map. So there's more like about shapes, like there's curves. But this one is like more straight on a different kind of like orientation, but like as a relation of the nodes in it, they are same, topologically same. And this is like 3 different like houses from Frank Lloyd Wright's works. So what is said by March and Stedman? So 2 of the houses were designed in the same year, and the 3rd one 2 years later. They might look different as a shape, but topologically they are equivalent. So if we check the graph of it, we might see the relation between these 3 different floor plans. What else? Yeah, so there is something also called spatial relation. So here I was talking about like a single shape. So a relation of a single shape with another single shape. So what about if there is like more than one shape? So these shapes could be like polygons, like closed surfaces, like line-based things. So there might be like not thousands, but like many relations between them. So that might be like being inside of another, like touching, like sharing an edge. Here is also sharing an edge, like one surface and one line. They can like cross, they can overlap and cross in a different way. And a similar kind of thing might occur in the three-dimensional objects. And this is by Steiny from 1980. A spatial relation is specified whenever any collection of shape is considered to form a recognizable arrangement. Okay, so one of the important thing is to understand the relation. So it shouldn't be like very ambiguous. But here, for example, with this A, we can say these are like detached. So there's a clear relation between them, and these are not detached, even the same shapes. So they are like sharing a point, and these are sharing an edge, and these are sharing a surface, like partially. It might also share the edge 100%, and that also define another topology, because like sharing it partially and like fully are different things. And here there's an intersection, but a partial intersection of the shapes. And here it's a full intersection. So the small shape, like the half cube, is in the full cube. So also there's like debates and like speeches of the Greglin, like the article of the Rick Oxman and other works by like Schmeier and Zeng in different years. So yeah, what is the topic? So like from typological to topological architecture. So there is other things to discuss rather than like typology. So what Rick Oxman said, like topological design is based on the exploration of topology and non-Euclidean geometry in creating the design media for formation. Okay, so she's like discussing the importance of topological design in the formation process of design. And here they are talking about the topological optimization, and they are thinking about the new methodology. So yeah. And the next term, homeomorphism, and it means like similar and same plus shape and form. So like similar shapes, like same forms, that kind of thing. So object of the same type, okay, I'm going to explain what's the same type, can be converted to each other in two directions. So one shape can be transferred to another one, and another one can be transferred to the initial state. Okay, so there is a like forth and back, not cyclic, but inverse mapping between these shapes. While this transformation, the topological structure that I already mentioned, is preserved. Yeah, so topological objects can be transferred into another object, and we don't have to tear, detach, bend, pull, and stretch it. And this condition called homeomorphism. So the square into a circle can be an example of it, or a coffee cup into a torus can be another example of it. So, but for example, transformation from sphere to torus doesn't provide a homeomorphism, because when you do it, like sphere is a solid. Sphere is a solid with a like proper inside outside, has a proper boundary. But torus has a hole in it. It's a complete different type of shape. Yeah, and there is a GIF about a coffee mug morphing into a torus, and there is a step-by-step visualization of this topological transformation. And like another, maybe another very famous examples of it is like the climb button and Mobius strip. And yeah, and the climb button is an example of a non-orientable surface. So it's like made of two Mobius strip. It doesn't have a like definite inside and outside. And yeah, and it doesn't intersect with itself. So it's a challenging shape to understand the topology better. Yeah, I think it was my part for now. If you want to add something, if you want to ask something, or if I lead something, please comment on it. Thank you very much.
Thank you very much. I think this image is so related with the thing that we will work on in the forthcoming days. So homeomorphic formations, everyday life objects intelligence is about also the household objects. So we are seeing a cup, which is a household object, or we are using it in everyday life, in offices, in outside. So everybody drinks something, right, every day. So the thing is, here we are seeing many objects which are same in terms of topology. So the cup is not different than the donut look like torus at the end. And all of these are named as homeomorphic formations at the end, can be named as homeomorphic formations. So I think, yes, this image is the most important image, Orkan Hoca.
I want to add something like it's not very related with our subject, but it's related with my previous work. It's the same thing is also possible for complexity. For example, like when you see something like visually, it might be like more complex, but when you measure it, like you might find there like similar complexities in different like objects or like built environments or like buildings in the cities or in the nature. So there might be different like levels of objects that you can explore. So there might be like many features in a single object. So yeah. So everything is not as we see. So that's the point.
Exactly. Why also this complex part is also important. As you said, topology root, etymological root is coming from topos and logos. So topos is linked to the surface and logos is also linked to size. So this is the size of the surface. So it is trying to understand the complexity and the nature, the essence of the geometry. And yet it's not interested in the shape. So what we see does not matter. The complexity level or the formation knowledge, it's information it requires, the formation information it holds is very important. So we will try to understand, for example, what kind of objects we have in our everyday life which are topologically same.
And I think this requires a level of abstraction in our brains first. If we just focus on the shape, without thinking it in a different way, without any abstraction, we might not see that. So,
exactly.
So like for example, like shape grammars are doing a kind of abstraction, like space syntax is making a kind of abstraction, like this topological analysis or like spatial relations makes this as well. So I think the abstraction and like to understand the like inner logic of it is the key here.
Exactly. And also I want to add one thing more. On the left side, when we are seeing this coffee mug morphing into a torus, this is also called a homeomorphic transformation.
Yeah.
So we are seeing a transformation here. And through the AI, we will try to understand how form transforms through its topology. And we will try to understand the two-dimensional information and how we can transform this two-dimensional information into 3D. We will try to also experiment with those. And for example, 0 is equal to, do you see it? 0 is equal to 9. And in this equation, 9 is equal to A. So 0, 9, and A, they all have a hole.
Yeah.
So in terms of topology, they're same.
Yeah, but B is not, because it has 2 holes.
Yeah, exactly. Exactly. Yeah. So this was also what we are talking about. It doesn't have to be just a, cup. So we will make some observations at home today. After the workshop, you will make some observations. We have done it before. So, please try to look also from this, abstraction level, as Orkan Hoca has already underlined. Also, this is another type of abstraction. So we are purely interested in the information which objects actually has in their essence.
So in this part of the presentation sections, I will be explaining the general idea and the brief explanations about the AI, machine learning, deep learning, and generative adversarial networks. Actually, in this part, I will try to make you understand where is the location of the GAN, generative adversarial network, where is the location of the generative adversarial networks in the artificial intelligence topic, actually. As you know, there are too many different topics and the terminology inside AI. Maybe you heard about it. We are right now, as it is a hot topic of these days, the AI. We see too many different terminology as artificial intelligence, deep learning, machine learning, neural networks, generative networks, etc. So what is the taxonomy of these terminology? We will focus on this. Before continue with the technical part, I will start with the history, a little bit history, brief history about it. Maybe you know this guy. He is John McCarthy, who is the first one coined the term artificial intelligence. Actually, these artificial intelligence topics or debates on artificial intelligence dates back to 1950s. The first, actually, there was a first workshop about the artificial intelligence in 1956 in Dartmouth summer workshop. Actually, we can see there all the fathers of the artificial intelligence in that workshop. Actually, they were there to discuss the artificial intelligence field. What is the artificial intelligence? They actually, on those dates, maybe they didn't know the name as artificial intelligence or machine learning, but they know the topic is going to be a really important topic in the future days. So they made too many discussions, actually, and also there were different approaches in the artificial intelligence topic as well. So these different approaches gives ways to different technical approaches as well. So actually, we will see in the following presentations how these topics are creating different approaches in artificial intelligence. And John McCarthy was the first one who used the artificial intelligence term in this artificial intelligence field. As I said, as you can see in the heading part as well, we have AI, ML, deep learning, generative models, implicit density models, generative adversarial networks, and style gun kind of. So we have kind of a taxonomy like this, actually. AI is a bigger web, the biggest bubble. And inside the artificial intelligence, we have different kind of techniques. And machine learning is the biggest, or how to say, the most reliable technique that we are using in the artificial intelligence field. And it dates back to actually at the beginnings and the end, beginnings of the 19th century and ends of the 18th centuries. So it is not that much a new topic, actually, the machine learning. It is using an error function, and this error function dates back to 200 years ago, actually. So it is rather old topic, actually, this machine learning topic, but we are considering it is kind of an automation tool right now, these days. On those days, actually, it is kind of a mathematical formula, and they are trying to make some predictions. especially actually they are directly trying to predict the orbit of a comet. Actually by Gauss and Legend are trying to predict the orbit of a comet. And these actually simple equation, least square equation, make a big change in our lives, creating the machine learning algorithms actually. So at the end, after the machine learning algorithms, we have a different approach, representation learning, and inside the representation learning, deep learning. Maybe we have to understand what is this representation learning. Actually, in the how to say, the conventional methods of the machine learning uses not the representation learning, but the symbolic representations of the problem. But in the representation learning, let's assume that we are trying to train the algorithm with the representation, visual representation of the fork. Let's say we are trying to train the algorithm with fork images. But how to represent the fork? You can create some symbolic representation of the fork, saying that if you see a fork, if you see an object with 3 tines, for example, if it has 3 tines, then we can say it is a fork. But being a fork, it doesn't necessarily having a 3 tines. Maybe it has 4 tines, maybe 1 tines, but having a tine is its feature actually. So rather than explicitly saying the features of the objects or the data, let the algorithm find out the features of the data. This is the representation learning. And how you can obtain this? By feeding the algorithm with thousands of images of the fork, then you can show the thousands of different variations of the fork, being fork actually. Then the algorithm starts to learn how to represent this fork actually. So at the end, we are coming to the deep learning. Actually, it is a special field in the representation learning. So I will continue from here. But before continuing with the technical aspects, I want to put this, actually, I like to show this in my presentations as well. This is by Pedro Domingos, and if you would like to read this book, I really recommend you to read as well. Master Algorithm, the name of the book. Actually, this classification makes it clear what kind of different approaches we have in machine learning. Actually, we have symbolic approach, connectionist, Bayesian, analogizers, and evolutionaries. Evolutionaries, you know that it is directly coming from the genetic algorithm side. So it is kind of an optimization part of the machine learning. And analogizers are directly using this similarity-based algorithms. Maybe you heard about it, KNN, K-nearest neighbor algorithm is inside the analogizers. It is directly looking at the similarity of the data. So according to this similarity, it is kind of making a classification of prediction, whatever. So for example, support vector machine, if you heard about it, it is directly coming from the analogizer, and it is looking at the similarity between, for example, 2 pencils, okay? So if they are similar, they are in the same group, for example. So Bayesians are using the probability. So it is the, actually right now, the most powerful method in the machine learning algorithm. It is said that like this, but it is technically a little bit harder than the other topics to understand, actually, to get the understanding of how it's working. And the remaining is the main, actually, different approach is directly coming from the symbolist and the connectionist. Symbolist is the conventional way of machine learning, conventional method of the machine learning. And Marvin Minsky is the one of the biggest supporter of the symbolists in those years, actually. In the first, when the artificial intelligence firstly appeared in the field, the symbolist approach was powerful. Actually, Marvin Minsky was right on those years because he is supporter because of the hardware limitations. Right now, we have really a big power of the hardwares right now in our computers and in even in the cloud, right? Like we will use the Google Colab from the cloud. We will use the hardware from cloud. So right now we have the ability to actually compute the data, huge amount of data. And beside of this hardware power, actually we have the data as well. With the advent of Google, as you know, with the Google images and the Google, we can get too many different data. We can gather too many different data sets as well. So this big data, we are calling it kind of a big data. And on the other side, we have a hardware power. And with this togetherness, actually, we can use the connectionist approach. Actually, connectionist approach is directly coming. Why it is connectionist? It is connecting the neurons. Kind of, you can think this kind of a similarity between the neurons and the connectionist approach. But the symbolic approach is directly explaining the actually the problem with the symbols. This is creating the biggest debate in the history of our artificial intelligence. So if you can see, if you know about the winters of AI, because of these different approaches, the winter of AI appeared in the history of AI, actually. But after a while, in these years right now, we are directly using the connectionist approach, I can say. So here, as you can see, this is the father of machine learning term, because firstly, the machine learning term is coined by the Arthur Lee Samuel. The work of Arthur Lee Samuel, some studies in machine learning using the game of checkers. He was trying to make the game of checkers as an autonomous game in this study, and he is the first one in this study using the term machine learning in 1959. So you can take a look at the paper as well, if you wonder. But the main important thing is that, sorry for making it a little bit Turkish and a little bit English. The main important thing is that we have to know the problems of machine learning. Right now, you can see three different problems of the machine learning. Once you understand what kind of problems you can solve with machine learning, then you can directly apply the proper algorithm in your problem solution. So, for example, here, the machine learning algorithms problems classified into three different approaches. One of them is supervised learning, unsupervised learning, and reinforcement learning. Maybe you know that reinforcement learning is learning the behavior, so we can use them in the game AI, skill acquisition, real-time decision-making, robot navigation, using the reinforced learning directly. In the unsupervised learning, actually, it is totally different from the reinforcement learning, but it is kind of have some similarities, or the clear distinction between the supervised and the unsupervised learning we have. So what is that clear distinction in between the supervised and unsupervised learning is the labels of the data. Once you show the algorithm this pencil, if you say this image being a pencil, so if you have a label as a pencil, then this will be being a supervised learning. But if you do not give any label, any name for this data, it will be directly becoming an unsupervised learning model. So in the unsupervised learning model, what you can do, actually you can make a dimension reduction of the dimensions. So meaningful compression, structure discovery, feature elicitation, and big data visualizations directly coming from these dimensional reduction problems. And the other side, clustering problems are really crucial in the unsupervised learning processes. Recommender system, as in the Spotify or Netflix, it is directly using this clustering problem, and it is directly targeting the marketing. So customer segmentation is an important task in the clustering problems. When it comes to the supervised learning, as I said, if you have labels for the input variables, then you will directly train your algorithms in a supervised method. So in supervised method, actually we have classification and a regression problem. In the classification, as you know, you may be aware of it right now, we see these kinds of problems anywhere we look in the web as well. So for example, image classification, customer retention, diagnostic, and actually it is not only using the supervised learning technique, but for example, autonomous vehicles are making some kinds of object detection using this kind of a classification method. And when it comes to the regression, actually it is directly coming from the prediction problems, market forecasting, weather forecasting, life estimation of life expectancy, population growth prediction. If you want to make a prediction algorithm, you may use the regression analysis in the supervised learning method in machine learning. So these three important problems appearing in the machine learning field. Actually, there is the fourth one, semi-supervised learning. It is in between the unsupervised and the supervised. So some of your data points are labeled with the labels. Some of them is not labeled. So this is called semi-supervised learning as well. So what is happening with the deep learning? Actually, deep learning is directly trying to mimic the biological neuron. So we have neurons, and in between the neurons, we have some kind of a transformation of the information. So to be able to transform this information neuron to neuron, we have an activation function. If for example, we have weights of the neurons, we have the sum of these weights, some values are directly coming from the neurons. And when we sum these weights values, and we will directly make it input for the activation function. If this sum is over the threshold, it will be directly activating the activation function and the neuron will be firing. So this neuron will be, if the neuron is firing in the correct way, this neuron will be important for our training session. This is the actually one of the first artificial neural network structure. The first artificial neural structure is actually created by Frank Rosenblatt in 1958. You can directly look at the paper that I put here. So the first artificial neural network is by Frank Rosenblatt, but there was a problem of this neural network, and Marvin Minsky is against this neural network. Actually, this is directly coming from the connectionist approach. And Marvin Minsky was arguing that this perceptron actually is not working very well. Actually, this is kind of making only linear classification problems, can be solving linear classification problems. But if it is a nonlinear classification problem, the perceptron cannot solve these kind of problems. Actually, explaining the nonlinear classification problems is really difficult, but linear classification is really easy. For example, you have squares on this part of the graph and you have circles here. You can directly classify this with one line, but there are some interesting actually data sets which cannot be classified linearly. For example, we have circles in that part and that part circles, and these parts are squares, and you cannot linearly classify these data sets right now. So perceptron cannot solve this kind of problems. But when you increase the layers, right now this is one layer artificial neural network. So perceptron is a one layer artificial neural network. But when you increase these layers of the neuron, then you can classify these non-linearly classified data sets as well, because it will be learning deeper. So where the deep is directly coming from the number of the layers of the neurons is directly referring to deep neural networks. And you can see the first layer, for example, is directly explaining or learning the representation of edges. And the second layer is combination of edges, is directly creating roughly the parts of the face. And the object model, the deeper details are directly coming from the last layer of the deep neural network. So right now we can construct the representation of the face. So what is deep learning is that actually. So if you increase the number of layers of the neural network, then you can obtain a deep neural network. Actually, the first work is by Geoffrey Hinton. So you can directly check the reference that I put there. So where is GAN algorithm, actual generative adversarial network? Generative adversarial network is located somewhere here. So we can continue with generative adversarial network. But before continuing with the generative adversarial network, actually I want to talk about generative models, okay? So that we can understand what is this generative models, and inside that we have the generative adversarial networks. As in the every actually machine learning algorithm problems, we need to have a data set. As I said, whenever we have the data, enough amount of data, for example, thousands of data, then the algorithm can make a function approximation and can understand how to represent this data, as in the example of the fork. So this P data is a distribution of a data set, but this data is a real data. For example, ages of the human in the world, but it is really a big data, so we cannot access this real data in our world. So instead of accessing to the real data, we are creating a small amount of data set, kind of 1,000 data we can collect, for example. So instead of gathering the real data, it is not possible. We are just partially gathering the data. It is called p-hat data, for example. So the distribution of the p-hat data will explain something about the real data, okay? It is just kind of a mirror, let's say. So this will be our training set for the algorithm, consisting of samples drawn from the distribution. So we have a distribution. What is distribution? Actually, for example, we have a graph like this. The tallest guys will be directly gathering inside this graph somewhere here. The shortest guys will be somewhere here, for example. This is directly creating kind of this kind of a distribution. So it is explaining our data as well, what kind of a data we are playing with. After you're creating your data, the training session appears. What you are training, actually what you are doing while training, actually the algorithm learns how to represent the distribution of this p-hat data. Yes. After training, we have a model right now. So this model is directly an approximation function. What is that? It is kind of mimicking the real data. So we are creating a function that is representing the kind of trying to represent the real data distribution, okay? So this P model is a result of the training. It is trying to represent the P data with a function. So this is called model. And it must have an error. If we directly, exactly create the p data function here, then there won't be any place to make a mistake for the algorithm. It means that it is kind of a rote learning and it is directly memorizing the data set. When it comes to a data sample outside from the data set, that means that the algorithm cannot detect that data point outside of the data set. So we let the algorithm make some mistakes. So that is the reason we are not directly 100% accurate P data model, actually. We are not directly using the P data distribution, but we are trying to construct a model of the P data so that the algorithm can make some mistakes, not to make a rote learning or memorizing the data set 100%. Actually, this is the general process of the generative models, how it is creating the generative process. P model is a generative model right now we have. But there are too many different approaches in the P model usage. One is that explicit estimating the P model. You may use this approach. You have a P model distribution and you may directly estimate your P model, but it has some disadvantages. What is disadvantages? For example, one of the models that is using explicitly estimating the P model, for example, you have one input. Corresponding to this one input, you will obtain only one output. But in the generate samples using P models, so it means that implicit estimating the P model, let's say kind of this, it is directly using, for example, one input, but it can be creating too many different outputs, okay? So it is not estimating the P model, but using the P model, it is generating too many different samples. And the generative adversarial networks is located under this generate samples using P model part. And this is directly coming from the, this taxonomy is directly coming from the Ian Goodfellows, who actually proposed the generative adversarial networks in 2014. He is proposing this kind of a taxonomy for generative models. Do not interested too much this kind of too deep terminology, but if you wonder, you can directly go to the paper of Ian Goodfellow and try to understand what's happening here. If the algorithms is using maximum likelihood, let's assume it is using a likelihood estimation process, and we have two different approach, explicit density and implicit density. As I said, fully visible belief nets is only creating one output from one input, but generative adversarial networks can generate too many different outputs from one single input. We can say that. What's happening between these two different models, explicit density models versus implicit density models? The explicit models, maximization of the likelihood is straightforward. Simply, you are plugging in the model definition. What is the model definition? The model approximation, or P model, let's say, of the density function into expression for likelihood and follow the gradient uphill. Actually, you have a parabolic function here. You are trying to maximize the similarity, let's say, okay? You are trying to maximize the similarity, and it is uphill, actually, the parabolic distribution, kind of parabolic function. And you are trying to get the top point of this parabolic function. So it is directly trying to do this, and at the end, we get only one, for example, sample as a result. But in the implicit density model, as I said, these models, instead of offer a way to train the model while interacting only directly with the P model, usually sampling from P model. It is directly starting from a latent vector in the implicit density model, and from this latent vector, it is trying to construct the structure of the representation, actually. So this taxonomy is directly coming from this description. So when it comes to generative adversarial networks, what is happening inside? Actually, as I said, generative adversarial network is creating samplings from the P model. So where this coming from, actually? We have a vector. What is that vector? Z vector, for example. This Z vector is kind of a noisy image. And from this vector, the GAN algorithm is trying to create the X image, for example, X output. It doesn't necessarily being an image data, by the way, but right now, to make it clarify, I will be talking with image data set. What's happening here? Well, why generative adversarial networks? Actually, generative adversarial networks learns high dimensional complex real data distribution. This is the biggest potential of generative adversarial networks. What means this high dimensional complex real data distribution? Let's assume that we have an image 28 by 28 pixel resolution. So it means that 28 by 28, just make a multiplication, and 758 kind of something like this. I may made some mistakes here in the calculation. It means that we have 700 and something data points right now. This means that this is our dimensions of the problem. It is directly coming from just one single image. Do not forget. Let's make a calculation here. I will show to you. It means that 784 different data points. It is called dimensions. And it is kind of, let's assume that this is a grayscale image. So we can create this kind of amount of data. But if it is a RGB data, RGB image, then we have to multiply this by 3 as well. Red, green, blue channels are creating the colors. So we have 2,352 right now different data points inside one single, actually this is the dimensions of one single data sample. But it is directly coming from one single image. As I said, we need thousands of images. For example, 1,000 of image, it means 2,352,000 values needs to be computed by generative adversarial network. I think this is showing the biggest advantage and the biggest power of the generative adversarial network. So it learns high dimensional complex real data distributions. And it generates real-like samples from the latent space. The latent space, the terminology latent space is the Z vector. And latent space, also called on embedding space, is the space in which a compressed representations of data lies. kind of, it is a compressed representation of the forks, for example. It is a it is noise, but it has some values that can be converted or transformed to the image of the fork, for example. But if we wish to change or reflect some attributes of an image, manipulating the latent space is more tractable. So, for example, if you want to manipulate the result image, you can manipulate the latent space, for example. But you cannot directly manipulate the Z. Why? Because input latent vector Z of the generator is so highly entangled and unstructured that we do not know which vector point contains these features that we want to create. Instead of manipulating the Z vector, Solal is manipulating the Z vector, we will add another vector C, for example, Z plus C. This C vector can be a label. For example, if we are creating if we want to create a face image, then it will be starting from a noise vector Z and plus, for example, label I. So we can say that you will be generating the I label. So we will add another vector here that is representing what we want to generate at the end. So what can be done with generative adversarial networks? Actually, most of the works can be seen, or popular works can be seen in images, image data, but we can have some computer vision tasks or natural language processing. So you can generate some voice, for example, by using the generative adversarial networks, time series synthesis, semantic segmentation, plausible image generation, image to image translations you can do. For example, horse to zebras, zebras to horse. Text to image translation is a hot topic of the guns these days. You can look at the examples of the text to image, text prompt gun algorithms. Image super resolution, image completion, video generation, video next frame prediction, music generation, changing some features of an image is some of the tasks that can be solved by using generative adversarial networks. Actually, here, what is happening? We have two different functions inside the generative adversarial networks. One is the discriminator, the other one is the generator. So the adversarial part is directly coming from in between these two competitors, let's say. So there is a competition in between the discriminator and generator. Generator is trying to fool the discriminator by creating some fake images. Actually, discriminator trying to detect if they are fake or real. That is what is happening in the generator adversarial network. So discriminator examines samples to determine whether they are fake, real or fake. And discriminator directly learns using the traditional supervised learning. It has some labels. The labels will be real or fake. So we have two labels for the discriminator model. It is a convolutional neural network, actually. So it is trying to detect the generated images if they are real or fake. For the generator creates samples that are intended to come from the same distribution as the training data. We have a training data distribution and generator trying to create similar distribution. It is creating kind of mimicking the training data distribution. The generator is trained to fool the discriminator. And this is the function. I won't get into details, but as you can see, this is the expectation of the discriminator. This is the expectation of the generator. 1 minus discriminator's generator Z. Actually, as you can see, Z, the latent vector is here. Generator is creating an output from using the Z vector. This is the fake, and discriminator is trying to find its error if it is real or fake. After actually completing this function, it is kind of a min-max game. Actually, what's happening here? Discriminator is trying to maximize the error rate of the generator, while generator is trying to minimize the discriminator's error function. So it means that generator is trying to fool the discriminator by trying to minimize the error rates of the discriminator. Okay, this is what is happening. This is the architecture of the generative adversarial network. The discriminator is here, as you can see, and here is the generator. Generator is starting from a Z vector, the random vector, randomized vector, and it is called latent space. And it is just increasing its size to create an image size, for example, 256 by 256 resolution. And the discriminator is taking this and the training data set in parallel, while discriminator learning how to understand the real data from the training data set. At the same time, discriminator is trying to detect if this image real or fake. Okay, this is a basic convolutional neural network architecture here. This is upsampling process. This is downsampling process. It is the other terminology. So maybe you heard about this image. It is sold really. Actually, this image was so expensive, and you can see the signature of the GAN algorithm here as the function that we saw. And when it comes to the generative adversarial network, this is just a proposed GAN's taxonomy by Wang. Actually, you can see the paper if you want to see. But there can be other types of taxonomies. Actually, there are different types of architectures of the GAN network, or different types of error functions, loss functions, that is calculating the error rate of the algorithm. So we will be using style GAN in the different architecture types. So I want to just show the location of this style GAN that we will use. Actually, the network of architecture category refers to improvement of the modification made on the overall GAN architecture. The progressive mechanism developed in the progressive GAN, for example. There are different of architecture in the network architecture. Latent space category indicates that the architecture modification is made based on the different representation of the latent space. As I said, the latent space can be solely just a Z vector, or you can add a C vector here. C vector, when you put the C vector, actually you can see the conditional GAN is an example of the C vector added GAN. And application focused GANs refers to the modification made according to the different applications. Cycle GAN is an example, and style GAN is another example. So other ones is the loss types. You can choose any other loss equation to solve your problem actually. This is a list that I made for listing the GAN algorithms. I found 626 different GAN algorithms, but you may find more than this, because this was, if I didn't remember wrong, this was from 2018. So this list is from 2018, but right now I think the number of GANs are really too much. And when it comes to style GAN is released by NVIDIA. Actually, it is GPU, as you know, and company which is releasing GPUs and the graphical processing units. And with the power of the NVIDIA, we can do this kind of really big computation as well. The style generative adversarial network, or style GAN for short, is an extension to the GAN architecture to give control over the disentangled style properties of generated images. Actually, they are saying that our generator starts from a learned constant input and adjust the style. So learned constant input is kind of using a transfer learning method we are using in style GAN. They are training the algorithm on face images, and then we are using directly these face images as a starting point of our training process. Input and adjust the style of the image at each convolution layer based on the latent code, therefore directly controlling the strength of the image features at different scales, they are saying. This is, for example, this person does not exist.com. Maybe you know this website. Actually, this website is generating too many always creating different faces which are not existing actually. This is not a realistic image. Where we can detect, actually, you can look at the background or you can look at the earrings. This algorithm is having some problems by creating the earrings. So you can see there is a problem in the earring part, and you can detect from the mount and this part as well. There can be some unsymmetrical images appearing in these parts of the face as well. And from the background, you can understand or detect if this is real or fake images. As you can see, there are some blurry part of the image, so it is fake actually, and this earring part is wrong. So you can say that this is a fake image. This is some hints for detecting the unreal images. And right now, this is a small video explaining this style-based generative adversarial network. So we can continue with latent space exploration. Actually, in the video, we see two different examples of the faces or the cars or cats actually. So how they are transformed actually directly coming from the latent space exploration. When you adjust the latent space, it is directly creating a new kind of a vector. So to create a new kind of a image at the end. Latent spaces provide a representation of data by embedding the data into an underlying vector space. Exploring this space allows for deeper insights in the structure of the data distribution and the relationship between the data points. And one more thing, the interpolation. Right now, there was a GIF, but I think it is not working right now. It must be interpolating in between the images. But if you can remember in the video, the images was smoothly morphing into one image to other image. This is directly obtained by interpolation technique. So these interpolation coefficients are used to combine style codes of two different images and semantically transfer a region of interest from one image to another. So in this way, we can see these smooth changes in between two different images. So it is creating kind of a transformation, continuous transformation in between images. So there are some different examples from the guns. This is kind of an trail. This is directly coming from my PhD thesis actually. This is Palladian grammar generation by using the generative adversarial network, the actual deep convolutional generative adversarial I used. Here, my objection was to create the plan schemes of the Andrea Palladio by using the Palladian grammar technique from the shape grammars. These were some of the results actually. This is another example from an actual course in ITU. One of our friends are trying to create a Turkish house with sofa actually. And we can see some samples from these actual results. In this work, actually, he used style gun, for example. In this one, the actually DC gun is not that much powerful when we compare with this style gun. Style gun is right now surpassing the all guns in terms of the realistic effect of the realistic generation of the images. So maybe you know this Stanislas Kailus, actually the reference is wrong, but Stanislas Kailus work, the Archie gun. NVIDIA released this kind of a gun as well, using directly reference from the Stanislas Kailus. This is kind of a three-step generation of the plan layout of an architectural plan scheme. So here they are kind of using pix-to-pix algorithm here to create this kind of rooms from starting from a ground level, for example, footprint. This is another one. We have a footprint of a Super Mario, for example, but by using the labels, these labels, as I said, a C vector right now, we have a condition. So according to this condition, the latent space is exploring according to the living room or bedroom or bathroom or corridor, kitchen or closet, for example. So it is creating within inside these boundaries, creating this kind of semantic parts of the image. So maybe you know that GoGun, it is directly using similar technique as pix-to-pix, semantically referring to the labels, directly explaining the representation of the results. So as in the Z plus C vector, the same thing happens, but the architecture of GoGun is a little bit complex. If you want to look, you can take a look at the examples. And here, this is a little bit right now famous VQ-GAN clip or the disco diffusion. You can directly use text prompt to create some images, visuals, and these are really fantastic and really powerful and fascinating image results directly created by generative adversarial networks using text prompt. These are some 2.5D examples, And this is using height map results of the generative adversarial networks outputs. These are some buildings, churches and skyscrapers used in the data sets. So they try to create, actually the student tried to create here in the course of ITU, student tries to create a combination of the skyscraper and the churches here by using the style gun. This is by Ayşegül Hoca. This is directly used in this one. Disco diffusion algorithm is used to create text prompts and to create visuals from text prompt. It is really an interesting result. As you can see, the text is a strange brutalist high house section of laborious woods in the sky, made of concrete, steel, and glass in the style of Ternabo Fujimori. So here we can see the results, one-to-one result of the image at the end. It is directly representing the text that we wrote here. Even it is detailed, specifically related to architectural disciplines, still it can create this kind of visuals. And these are some style transfer in 3D. You can take a look at this paper. So they are directly using the sections or the sections of the generated sections of the architectural entity. Then they are morphing actually these images into 3D. And real 3D gun can be said this is the earlier examples of the 3D gun, but it will be coming in the near future, I think. The main disadvantages of these 3D guns is the actually data size is much more bigger than the 2D examples, as these are voxels right now. It needs to add another dimension to these pixels right now. So it is adding another dimension. So we need to have highly computing powers to calculate these kind of training processes. So this is another example, for example, but again, the GIF file is not working somehow. The living portraits, actually the algorithm is trying to make giving a life to the portrait. The Mona Lisa was smiling here while shaking his hands on the right and left on these images. But if you wonder, you can take a look on the web to see the GIF result. This is actually recent result by Google. Imagine, maybe you heard about it. Maybe it is almost 1 month the Google released this algorithm, and it is really creating cool results at the end, really realistic results. For example, a photo of Shiba Inu dog wearing a sunglasses and black leather jacket riding a bike in a garden. One-to-one mapping the text to the image we can see, and it is realistic result. And again, it is kind of turning on your eyes. If you have a turn of eyes in your photos, you can directly apply this gun algorithm to turn on your eyes actually. So it is interesting. And the most delicious gun is the pizza gun as a result. So even they create a pizza gun to create some ingredients for them. For example, you can add on your pizza some olives, or add pepperoni, add corn, or you can remove them. You can adjust your ingredients of your pizza as you want in this pizza gun. It is delicious. So at the end, actually this is criticism by directly Ian Goodfellow's paper. He is saying that after all, when applied to images, such models seems to merely provide mere images, and the world has no shortage of images, he is saying. So why we are using the generative adversarial networks then? Actually, he replies this question as well, as the world has no shortage of images. We have thousands or billions of images over there in the Google or anywhere you want. And we are creating the images everyday life by using the smartphones as well. So the main important thing is that generative adversarial networks has a really big power of manipulating the high dimensional data, as I mentioned previously. And generative adversarial networks can be generating or predicting some missing data as well. And a single input may correspond to many different correct answers too. and realistic generation of the samples from distribution right now possible with the generative adversarial networks. If your task is related to the art creating, and artwork gun is over there, it is kind of a art creating tool right now, and image to image translation and more different tasks can be solved by using generative adversarial networks. So it is not only creating images, but it is creating some solutions for some specific problems.
There is a website where you can play with a generative adversarial network, and I'm going to send it through chat right now. And here, what we will see, we will actually see the real-time interplay between the generator and the discriminator. Janojo has already very detailed way explained those, but how it works, actually, those two, things, generator and discriminator, compete with each other. So the generator tries to convince discriminator the thing that I'm generating is real, and the discriminator is buying it or not. If it is saying, oh, okay, that's real, then it's going with the real, but then it's saying, no, it's not real, it's fake, then the system is go and go and go, so it's like a loop. And now when we hit play, we will see how the distributions of the real and how the fake is trying to learn the distribution throughout the process. And you can examine also by using a pre-trained model, the data distributions from here. We can fast forward.
Maybe I can add something here while it is training. The purple ones are trying to find the locations of the green points right now. The green points are the distributions of the real data, as you can see. So they are trying to, actually the purple ones are trying to converge to the green points right now. What's happening here is that.
Here also you can see in a more detail, more explanation. So this website is a very good website to understand the content of GAN and how it works. Here, for example, we are able to see the data distribution in a more clear way. And now the fake ones are trying to learn its distribution. They're getting closer to it, so they're learning. And also, I sent the living portraits GIF. I think this was lovely. This work to see again online. Okay. So this is kind of a game between the discriminator and the generator. After discussing AI and GANs, now we will talk about data gathering and processing, and how we will collect data and how we will prepare it. So if you remember, before we gave break, Kumsolo just said that, are we copying, or we can we copy? So this was like a debate. So there's a guest about, we are wondering about, can we copy? I mean, copying is very bad, right? When you get into the system to the undergraduate level, everybody says that, oh, copying is really bad. You have to find an original, a unique idea. It should be really unique. So, throughout the AI process, from the presentation, the style GAN is like mimicking the style. It's trying to learn its style. It's trying to actually distribute it according to the needs, and it's trying to create a familiar or a very almost familiar thing. So we need to think about this also. Is it copying, or is it actually not finding something new? Now we can also discuss it after this session. So this session is not a lecture totally, it is actually a tutorial session. So now we are entering to the tutorials, and it's an easygoing session. And first of all, I will talk about data sets. So what kind of data should we use and how we can reach this data? And we said that Google is actually a very good data set pool when you look at it, but in terms of AI, you need a really huge amount of data and many images, in other words, and you can reach those data via some, websites. There are so many actually, but I will show some. And afterwards, I will also talk about how we can generate our own data. And one of these websites is Kaggle. You can find some data sets. When you click on it, I'm going to also now send the link to you. You can see that there are some keywords, so all of them are labeled. And for example, let's get into cats. When I write cats, it found 448 data sets. And as you see, there are various data sets related with cats versus dogs, or cat and dogs, or natural image. So all these data sets include cat data somehow. And you can actually go into these data sets. You can reach to the context, and then you can download the data set if you want, or you can use it and you can look to its ingredients. It's actually features, what kind of data sets you're looking for. I don't know, but you can, for example, write architecture. And for architecture, actually, there's not much data set out there. There is, but still, it's a really huge gap. We need to create a reliable, a good data set for architecture. So here you can see some of the styles, and you can reach to do photos, images, and you can also look to its, again, ingredients. And Kaggle is one of these websites, but it's not the only website. Also, there are other data sets and other websites where you can reach data very easily. One of them is ActiveLoop, and here you can also reach from the dataset panel. I'm gonna again give directed the links. Also, it is explaining how this system works. So this is like a hub, for example, and it's linked to the GitHub also. And for example, we can look to Coco dataset, which is one of the famous datasets. Also, MNIST. MNIST is a dataset which is very important in terms of digits. We are seeing some digits, handwritten digits, and this dataset is used for especially for testing the models. And ImageNet data sets, again, you can reach the ImageNet data set from various websites. So I'm just showing you some of the portals. And ActiveLoop has also an application. Also, you can use some of the applications here. And for example, let's get into one of the applications. Since we will use FFHQ, I will explain this in detail. Let's try to open the data set. So FFHQ is Flickr Faces HQ. This is the abbreviation. It is consisted of human face images, and it is actually it has been used throughout the AI process, especially in deep learning for GANs as a starter. So this is the data set where we are starting to build upon it while we are trying to train a model. You can start from scratch, or you can use a pre-existing data set. Why using a pre-existing data set matters. Actually, this comes with a knowledge. So there are too many informations inside of these images. So you can, you're able to take out this information and you're building upon this information. So that's why it's important. And here you can also see some of the visualization settings, and you can play with those as well. And well, FFHQ data set also has been, underlined in Tara Karas, who are the Karas et al. Actually, there are other people also, Simona Lane and Tim Elia from NVIDIA, who are the creators of the Stalgan 2 ADA, which the algorithm that we will use. And we are using a FFHQ data sets 1020 to 1020, and it should be in a rectangular format, and it should be RGB. So these are very important information. And what we do is, first of all, for example, this is another workshop I attended in Sigrade conference, which is the workshop was led by Mohammed Bejru. Also, he has another session in Digital Futures. And here I wanted to work on films and Miyazaki films. And I tried to extract some of the frames from the films, and I created a processing code to take out the data out of it. So the previous websites are websites where you can reach to Redis data data, but also you can create your own data. So today I will talk about how you can create your own data, how we will gather the data, because for the workshop, you need to, after the session, you need to collect some objects, and then you will start photo shooting, and I will also explain that in a more detailed way. And after collecting some data, you need to process it. You need to actually crop it, resize it, and afterwards the training session will start. So those are all images which are generated by using Stalgan. And in the workshop, so what kind of data we will use? You are seeing some of the photos taken by me and by Canuzum in the beginning of the this workshop planning. So we try to take, household objects, and we try to photograph them from 16 angles. And in order to understand its rotation, we put a white background, and this is working like X and Y. You don't have to do it, but we actually suggest you to put a white or beige or a simple background for your objects while shooting your photos. And as you see, the scales of the objects really differ from each other. So I collected, also Janoja collected the objects in the house, which are working in terms of topology. So they do share the same topology. And then we try to generate the homeomorphic formations out of it. And here you are seeing cups, but those are not cups. So this is used for eggs and vases, and their forms are different from each other, yet they still share same contents in terms of topology, as we have already underlined it. And then we will go on working on the Stalgan 2 ADA. The training session will be tomorrow. So today, the data gathering session, we will give you an assignment, is very, very important, so that you will start to train your model tomorrow. And the data has to be ready for tomorrow. So here you are seeing a variation sets, which is one of the iterations of the model. So new cups or new vases are emerging after training this. For example, this one doesn't exist, but now after giving the data, which I showed you previously, the Stalgan 2 ADA started to generate the new cups or new vases. And here we are able to see the new generations. And this took 12 hours to train. And also, hopefully you will train it at least 12 hours. Well, this is just a 12-hour training, and you're seeing the transformation between the objects, and it's creating new objects by trying to mimicking the registry ones that I showed in the data set before. And we are seeing a triangulation video here, which is an exploration in latent space. And here we are seeing a projection of the style. So we have two cups generated by the style again, and we are trying to project one of the style onto the other. So during the workshop, hopefully you will be able to generate this kind of objects at the end of the workshop, starting from tomorrow. And what we should do today is you will look for the everyday life objects. If you are in a house, you can find household objects, cups, plates, etc. with the same topology. We have already discussed this. And you can shoot it with a photo machine or with your cell phone. You will capture the formal topological contents. Minimum, please use 8 angles and try to shoot the photos from elevation and a little bit from the top. And then you will crop and resize the frames, which I will show it to you through the GIMP. Also, you can use other softwares like Photoshop or any other softwares which you prefer. But the thing is, using GIMP is really practical, because here, for example, we had almost 520 images. When you have 1,000 image, 3,000 image, I mean, processing it really takes time. So I will try to show you this process. For editing the photos, there is batch image manipulation for GIMP. You can download it from this link. Okay, I will, oops, okay. And I will try to show you how we're gonna proceed. So as I told you, I had cups, and I separated them into 2 folders because as you see here, there are some small ones, and I will crop them in a rectangular shape. Why I'm cropping it in a rectangular shape? Because the data set, FFHQ data set that we would use is in a rectangular shape, and all the weights and all the information has to be same. So the channels has to be RGB. The resolution we will use is 1:22, 1:24. So this part is important. And when we look to the mid-big, so I put in terms of scale, the mid ones and the big ones. For example, this was tall into another separate folder. And I proceed like that. And then we have the edited cups here. And what you need to do is pretty simple. By the way, check out how many I have here. Here we have 96 and we have 542. So it will take too much time without those softwares. So when you open the GIMP, you will see the file. This is a very, very simple process. So file, and when you upload batch image manipulation, when you click on it, you will see a menu will be pop up in front of you. Okay, are we good to know? This is a very basic thing, okay. Here, you can add some manipulation sets. So it's working like a set. It is like action in Photoshop. So for example, you can resize it, you can crop it. So when I click crop, you will see that 1:1. And you can also manually crop it, but I prefer 1:1, and I'm saying center, okay? And then I say, okay. And then I can add resizing. So you can resize the width percentage or pixels. Here, for example, I can write directly 124, 124. After cropping it in a square format, we can resize it to 124 to 124. Let's check out what is the information we have here. Go right click on it, say properties, and come to details. When you come to details, you will see the information of the image here. So the dimension of this image is huge. It is 4032 to 3024. And it is 72 dpi, and you can also see the color representation. The channel is RGB, so that's cool. And I will say, okay, I'm not changing anything else. And we have the cropping and we have the resizing. Now I'm coming to the output folder, and here, maybe I will add another folder here. Cups edited too. Oops. Okay. Okay, so output folder will be cups edited too, and we want to add images. So when you add images, it's asking you add single images or add folders. I'm going to add folders directly. I will start with the small ones, and I'm adding all the files into this one. Then I just click apply, and it will start proceeding. You need to be patient. It can take a while. If you remember, I had 93 images in the small folder. So it will take a while. When you have like 1,000 or 2,000 images, it is taking actually maybe half an hour. It's actually due to the number of your data. Are we okay? Everybody, maybe you're trying your own, or but you don't have data right now, right? Maybe you can upload some data from the internet and you can try it if you want, or you can try with the folders you already have in your laptop. Also, another important thing, especially while renaming power rename, I'm using power rename for the data, and because naming can be really hard sometimes, and you can upload it from this website. Okay. Let's see how it goes. Okay, it's proceeding. This is ended, and almost 400 and 500 images minimum you need. Normally, it is better with thousands, 2,000, 3,000, but we don't have much time to create the data set because it's taking time. And afterwards, minimum 5,000, 4,000 will be okay, Susanna. Okay?
Okay, thanks.
Now it actually finished the process. So as you see here, I have the objects. By the way, this is very small. Do you see? Maybe it is better to have it more close. This one remained very small, but then while you're taking the photos, please try to be aware. Also, we had this problem. Please try to be aware about the cadrage, the framing, okay? And maybe you can try to position it in a better place like that. And the resolution matters. So if your cell phone is not taking photos very good, I mean, try to find something else because resolution matters. Resolution is important. And then here I had too many images, let's say. For now, I will work on this. I'm going to change their name. There are multiple ways. One is press F2. And you will just write a name and it will change actually, for example, cup. Okay. But what I'm doing here is I'm right click on it and power rename. And in power rename, you can, for example, manipulate the names very easily. I'm gonna erase cup and I'd like to change it with 0, 0, 0, 0. And I say rename. Now everything looks cool, but I don't want parentheses here, for example. And I'm coming here, power rename, and I'm saying that I would like to erase the space here, and I don't want to use parentheses. Now I'm just clicking on it again. And then also I don't want that one. As you can see here, you can use different kind of options. I'm using match all occurrences. You can enumerate them. You can select some of them. The logic is quite simple. So imagine you have 1,000, 2,000, 3,000 images, and this becomes really, really handy. And in some of the algorithms, you really need to name it very precisely. In our SALGAN2 ADA algorithm, you don't have to rename it, but I just wanted to show you because maybe you will find other algorithms after the workshop, and this part for data preparation is highly important. And then just right click on it and look to the properties and come to details. You will see that now it is 1,000 to 200, 1,200, and it is in RGB channels, so everything seems fine. Okay. So why this is important? Well, I'm going to show you another data set. Which was the data set of the arterial landscapes of Miyazaki. So, and it was huge. So why it matters is you're seeing frames from a film. And if you will use this as a data set, as you see, you have 400, okay, 4,503 images. If you are using another programming language, maybe processing Python, you can also generate those data by using another algorithm. Also, you can use Google Colab. But the thing is, naming matters. It has to be really precise, clean, and you need to use a clear method. And the ones I showed you is working very well for images around like 400, 500, 1000. But if the data set is getting really bigger, those, using GIMP or using Photoshop will not work either. It will take too much time and it can collapse in one time. So for today, for this workshop, we will use this method today. So what we want you to do is check out the objects, household objects, or outside. It doesn't have to be inside of the house. It can be outside. You can go to the street. You can go out. By the way, you will both have fresh air after having this Zoom session, which was a very dense session, by the way, because it was loaded with the lectures. So you can check out the everyday life objects in terms of topology. Take a picture of them, okay, at least 8 angles, and try to have some, like, not elevation, but almost elevation, and try to have from a little bit from, not top, but a little bit angular. I'm going to show the angles again too. Yes. Like that. Also, for example, yeah, those are others. Yeah, our example can be a little bit boring, by the way, okay? So we did it at house, so you can find more interesting objects and you can experiment with them. So those are some toys from my boy, and also where are the others? Here, for example, I came closer. So try to take the picture from a distance and try to use high resolution. And while cropping, please group it. I mean, you can't crop all the data all together, as I showed you before. If you do not change anything, it will become too small. Now, maybe you want to get some more closer and you want to recrop it again. And you can generate some stuff by using your own. Maybe you have some toys at home. You can generate your own objects if you want. And this was another try, actually. We try to take videos, but this is not working very well because you are losing resolution. So do not try taking videos, okay? When you have the snapshots, if your cell phone or if your tools like sorry. So shooting videos is not working very well, but
I should read another question. Actually, 2 questions. Can you read them, or should I read them?
Yes, I read it. I read it. Okay. Sorry, I would like to confirm the number of photos again. How much we need to take? We need to take 400 or 500. We need to have at least between 400 and 500 images. Okay. This is minimum. It can be more. And could we combine different size objects? Yes, we can. Again, I'm showing it to you. Here we are seeing, this is, for example, in terms of scale, this is a very big vase. And this is a very small object. And I combined them, but how did I do? I splitted the data set into two while I'm preparing them. Then I joined them, okay? Then I joined them in another folder and I renamed all the files. And here, yes, I was looking for those. Those were the objects. Janoja has photograph, for example. The settings was different. So please try to keep the settings same. And we worked as a group. Let's say we were 2 persons as a group. And I'm gonna stop sharing. And I want to look how many people we have here. 12. Okay, I think you can work in pairs or you can, yes, 6 group, we will have 6 group. We can do it like that, right? Two people will be good or 3? 2 will be good, okay. So you will become a group. Please try to select a group member. And by the way, we have a Discord channel. You can always talk with us through this Discord channel if you have any questions, okay, after the sessions. And also you can work throughout using Discord channel or WhatsApp. In the previous workshop in DigitalFUTURES, we worked with WhatsApp and Zoom as a group. We were from Turkey, Hong Kong, New York, so we had, you know, some time differences, but it worked very well. The planning is up to you. And
before we leave, we can just decide the groups.
Yes, also that can be. So again, I'm resharing it again. What you need to do today, you will have day 1, assignment 1. It is the preparation of the data set. So, oops. You will have an initial idea. We don't know what will be your initial idea actually. We set topology as a starter, but maybe you will have other ideas as well. So think about it. It can be something original or not. It doesn't matter. So do not feel any stress on you, but at the same time, try to benefit from this so that you can experiment with some, you know, data, and you can see the differences between the different data sets. And you need to collect some objects, and then you need to take photos of them, at least 8 angles, as I showed you before. And then you will, after capturing the 8 angles through the topologically same objects, you will crop and resize the frames, and then you will zip it as a file for tomorrow.